presenter will be here.
Good evening, ladies and gentlemen. Ooh, that's loud.
Can everyone hear me okay? Thank you, Howard. Welcome. Tonight is a very special night for the Math for America community. This is our second annual Master Teachers on Teaching event. And the subject tonight, or the theme tonight, is change. And that change can be interpreted and was interpreted by our 7 unique presentations in many different ways. But I thought it's particularly appropriate for many reasons. This year and the last few years as teachers, we've been bombarded with change, with reforms and curriculum and the way we're evaluated and our expectations in the classroom. But more importantly for me, I think that as teachers every day, we are responsible for change. In many ways, learning is a transformation or a change. And so I guess one of our goals for tonight, in addition to welcoming all of you and honoring all of you, is that we all leave perhaps with some change having occurred in the next hour and a half or 2 hours. So that's a humble goal. Before we get started, we have to go over a little bit of housekeeping. There's no food or drink in the auditorium, and it's hidden well. I feel like there's a dumpling somewhere in here. But. Ed, do you want to bring up the slides for the bathrooms and stuff, or you want me to just talk over those? All right, first things first, many of you have already been in the auditorium, but each one of your chairs has a microphone. For those of you in the front row, it's on your side, or in the aisle, it's on the side. Everyone else, it's right in front of you. Clearly, they did not make this auditorium with teachers in mind, because you address rooms full of people all the time without a mic. But what you do want to make sure is that that's off, or else we will hear your stomach grumbling or you're whispering to your neighbor. So make sure that's off. And if you need to use the restroom, there are restrooms over to the right. And the exits are also that way. There's an exit through here and right out the back, and also the stairs that many of you came up. So that is the housekeeping. And without further ado, it is my honor to introduce our first presenter. Sean Arichello teaches 8th grade math at the Salk School of Science nearby. And to be true to the theme of change, he's a brand new 2013 master teacher. And he's going to be talking to us tonight about expressions of change. So welcome, Sean.
Okay. So one of the major themes of this project is to help students get excited about the change they see happening in graphs, because I feel like if we can get students excited about what they're studying, then they can understand what they're looking at. And the way we're doing this is by helping students connect mathematics with comedy and performance. And this is not a connection they're willing to accept, the fact that math could be funny or somehow be involved in performance. But I say, why not? Because math is something we use to describe the entire universe and things beyond. So why can't we use it to describe some humor? Why can't we use it in our performance? Really, though, I think this project is about developing student intuition around the visual change they see in graphs. Visual, because I feel like that might need to come before some of the complexity that we add later in our equations and graphs and that we add with our numbers. So we're developing this intuition through storytelling as a stepping stone into getting into more complex mathematics. It's also really, when you have comedy and performance, it's a really group activity. It's a wonderful activity for the group to laugh together, to act together. And if everyone around you is getting the joke, it's just natural to want to know what is funny about that joke and what's happening in the change in that graph. Right? And if you're like me and you're usually that last person to laugh, or you're just struggling to figure out what's so funny about what's going on around you, you're asking the right types of questions. You're ready to learn about the change you see happening in the graph. And also, I think it's wonderful because this type of work, I think, can really encourage students to play with mathematics, which is something I think is often a struggle, right? The resistance against just going into your algorithm and solving the work. So a lot of my work this year around this visual process and change is based on some of the wonderful work I found on different blogs. Specifically, I would point you to Dan Meyer's blog. If you haven't gone there, go there. He's got some great ideas on using graphs. And another one is Mary Doom's blog, Curiouser and Curiouser. From them and others, I realized that one great way to get at change is to introduce graphs minus numbers and variables. In this icebreaker activity, and any of these graphs I think can be used at any time in the year for any unit, the goal is to put your name next to a point, right? Maybe it's an icebreaker activity for a group of 4. You put your names next to the points, and then you assign values to the axes that describe in a non-derogatory way, staying away from physical attributes, why you fit where you are. So I showed this to the students, and I thought, okay, they're going to tackle this, they're going to put their names on there. They didn't really listen, right? They went in a different direction. And I really like where they went with it. One interesting thing that they did with this was to use color, where they add blue and red on the axes right here. And they realized then where the blue point and the red point must go. And they also inferred how purple could be in both locations. Now, when this happens, when they tell this story, you are now able to ask all types of questions. You can ask them, well, where are the other purple points? Where are the bluish points and reddish points? And they're ready to listen because this is their creation. I found myself talking to them quickly about linear functions of purple and regions of blueness and of redness and blueness. And that's all stemming from this visual intuition. Other students took a more comical approach, although they took it very seriously, but I thought it was comical. Thinking versus doing. You've got the daydreamer, Lots of thinking, no doing. Careless, lots of doing, no thinking. And then the 2 remaining points are so extreme, you can't help but notice the middle school mindset, If you're not doing and thinking, clearly you're sleeping or dead. The opposite of that, in true New York style, is the hardworking individual. And as a class, we can talk about all the points in between. Another fun graph to give students is this blank bar graph, A and B. And it's like a gentle introduction, into this negative correlation, grades versus parents' anger, and all their hands go up and they're talking about negative correlation in a way that they're just infuriated about. Why are my parents always angry at me if I don't perform at a certain level? And all other types of negative correlations pop out. One of my favorites was to give them a blank linear positive correlation and ask them to assign values to the axes. And one that got us really thinking about how funny this could be is when students posted money versus problems. And before you know it, the whole class is talking about why this is or isn't true. So then as a teacher, you can just flip things around, And they're raising their hand and saying, well, that's the American dream, Getting more money, no problems, but we don't believe that. And they talk about this and they debate it. And then, although they're in 8th grade and never have seen a parabola, You can throw this in there, And here they're saying that's the plight of the middle class, And then they're talking about the 50s and 60s when the middle class had it really well. And, there's all these things come out because they're telling a story with the graph. And I think they're ready to talk about the change they see in a more formal way because they're joking around with it. Food comes up all the time. I actually didn't write this one, even though it does kind of reflect the way I think, which is the more cupcakes you eat, the happier you are. And this is where some of the performance comes out. Students can plot a point and say, well, how do you feel at that point? You haven't had many cupcakes, And they can act it out. And then we animate the points and ask them to act out the change that's happening in the graph until they reach this bliss point. And I thought everything was going great until one student raises their hand and says, that's not what happens, You can't just keep eating cupcakes forever. And before you know it, everyone's talking about where is your turning point? How many cupcakes can you actually eat before you get sick? And the parabola, again, is really interesting, and they've never really seen it. And we debated this one a lot in class about how accurate it really could be. But it was interesting to hear how the students tell the story here, how their energy flow throughout the school day. And it was interesting because without number, they so clearly understood what this point was right here, the turning point. I asked, well, what happened? Why is your energy going back up? What's helping you? Sugar, That's because we have a little candy cart that sells candy by our school that we can't get rid of. And, well, the sugar is pumping them back up. And they're talking about change and graphs in this visual way. It was funny, I was sending the presentation to Noah, and I had so many graphs I wanted to share with you. You can find more on this website that I set up called Student Graph Stories. I can send more to you. I definitely had about a 45-minute presentation. I would get very excited about these stories, and a lot of them I think you'll find interesting because I posted ones where there's a lot of misconceptions as well. I thought there were really some great teaching moments available here for you. As I move forward, I'm really interested in pursuing this idea of performance and graphing. So looking forward, I'm going to use this site as a model. It's another Dan Meyer project. It's called Graphing Stories. And I love the premise of this site for a couple of reasons. If you're curious how it works, the way they set it up is that there's a basic handout. And on the x-axis, they always put time, and the y-axis is always blank. And then you could choose a video appropriate to your curriculum. Students watch the video and then estimate what the graph would look like. Here's one example. So my goal is to help students. We'll model these with the students, right? Where you set up elevation. In this case, the hill is about 15 feet. And we're going to model this with the students and eventually get them to make their own performances in these types of videos. Because what's so interesting is not just the fact that students try and attempt to graph the time, is that they get so overwhelmed by the precision of the graphing that they forget the value in the estimation. Like, clearly, we're not giving enough information to graph this precisely, right, but we can still graph it. All these videos show it in half speed, but I'm going to scroll ahead to the actual graph itself. Because I love talking to kids about what the graph might look like, right? Going down the hill, the pause in between, and then back up it. Because I always find that there's some number here, but because we're allowing them to estimate, they're able to talk about how this is not necessarily a linear process. How when he's rolling down the hill, he's turning, and there's this brief rest period between, and then running back up the hill, they're changing speed. And there's a lot of disagreement about how accurate this graph is versus theirs, and that has a lot of value as well. And this is all, again, a stepping stone to more precise calculations. So as for the comedy part, I came across the work of Demetri Martin, and I've been trying to incorporate it. And what I think he's really shown me is that you can use the math to express whatever your joke is. And so moving forward, we're going to try and have students use specific functions, right, in a more detailed way to tell their joke. Here he is using a cubic function to, I think, really get a crowd cracking up.
Now this is a graph. Okay, karaoke. This is how fun it is to watch the person doing it. This is how bad the person is at it. It's kind of an interesting curve, because if they're not that bad at it, it's kind of fun to watch. You know, they're kind of singing on key or whatever. Not great. If they're a little worse at it, it's terrible to watch. It's like awkward, it's not bad enough to be funny, not good enough to be entertaining. But if they're worse, something magical starts to happen. The worse they get, the more fun it is to watch them struggle. Tone deaf, standing on a chair. Yes, this is what we want. What's interesting is skiing follows the exact same curve. Almost in the Olympics. Never been on a hill before.
So, with these type of graphs, my thinking is, even if we just show them the joke and then we want them to investigate the cubic function here, we could have them play with the numbers and then connect it to the graph to make sense of how when you change the numbers, you also kind of bend the meaning of the joke. So perhaps, we can set something up on Desmos or GeoGebra, have them play with the numbers, and the joke itself is just kind of an entry point. I think it makes a lot of the complex analysis enjoyable. You can think about how changing these numbers changes the meaning of your joke, right? And you're combining the intuition with the change you see in the graph. So looking forward, working with more performance, more comedy, even though as a math teacher, telling jokes is not really something I get to do commonly. But I hope to really help bring math into a place where people are willing to use it to tell stories that are worth hearing. Thank you very much.
Fantastic. Thank you, Sean. Next, in the spirit of change, we're going to hear from a master teacher of science. We're very excited to welcome all the science teachers to Math for America this year. And so it's my honor to introduce Nicole Maller-Sa-Variego, who's going to be talking to us about disrupting homeostasis.
Hi, everyone. My name is Nicole Maller Savariego. I teach at Vanguard High School in Manhattan. And as Noah already mentioned, I'll be talking about disrupting homeostasis. So homeostasis, I'm in a room full of science and math teachers, so I'm sure right now you're probably imagining or thinking of a phrase that goes with this word homeostasis. Maybe it looks something like this, right? We have a balance in our body, unchanged, seems pretty healthy. And now if I flip the switch and I go to disrupting homeostasis, many of you are probably thinking of something like this, right? Again, physical changes in the body, usually a bad thing. But today I'm going to be focusing more on disrupting homeostasis of the mind, which can actually be a really good thing when it comes to teaching. So I want to change the way you think about your teaching today. I'm going to start with a little story about two teachers, Teacher A and Teacher B. Both of them teach the exact same subject area. In this particular case, it's living environment. The exact same unit, anatomy and physiology, but you're going to notice two very different ways that they go about teaching these units. So let's take a look at Teacher A first and how they introduce this unit. Looks pretty standard. Teacher A passes out a syllabus on a Monday, and as you can see, they start on Monday introducing the unit using a PowerPoint. Okay, a little teacher-centric, but that's all right. And they assign a homework assignment straight from the textbook. Again, pretty typical. Homework, read chapter, answer some questions, and repeats a couple times throughout the week, and then maybe incorporates a lab if they have a double period. I want you to take a look at Teacher B, however. Teacher B, welcome to medical school. Greetings, your professor has assigned you and a team of medical students to conduct research on the following 4 health conditions: sickle cell anemia, HIV, pregnancy, and diabetes. Notice there's a narrative-like quality that incorporates the second person, you, which kind of engulfs the students into the story. And this story doesn't stop on the first day of the unit. This story will continue. Students will graduate medical school, move on to the Hippocratic Oath once they graduate, and then from there, they attend a residency program at my school, which is Vanguard Hospital. And it's going to be here throughout the entire unit that they now have to diagnose their patients, okay? So that brings me to the lab aspect, right? How do you diagnose a patient? You do labs. But Teacher A, their lab for the urinalysis looks very, very traditional to some degree in that it's following a typical lab report. They start with a purpose, maybe some background knowledge. You'll notice here it says the student will test urine, okay? And they continue with the materials, and they continue with the procedure. Probably looks like a lot of labs reports we've seen before, maybe a data table and then a conclusion. And typically, the student will then hand this work back to the teacher, and the teacher hands their work back to the student, and the student probably never looks at it again, right? They move on into digestion, circulatory system, etc. Now take a look at Teacher B's approach. Teacher B continues the story. And when the students get the information from the urinalysis, they're going to use that information and then continue it into lab 2, which is a digestive byproduct analysis on their patients, and a BMI analysis. And then their results from this lab connect now to the third lab, which is the circulatory system and blood smears, okay? And this goes on and on and on, so you can see the blood smears, for 4 more labs until they finish the whole unit, and it's one big story. And it constantly reinforces the curriculum that you're trying to cover for your students. Now, there's one last piece I want to touch upon that's different between Teacher A and Teacher B. And it's that age-old question we have, unfortunately, we cringe at, which is, why should I care about this topic, miss or mister? And Teacher A's responses were often, because you'll need this in college, or, well, let me pull up some statistics for you and show you why it's important. But Teacher B doesn't need to really answer this question. In fact, it doesn't come up very often, because prior to starting the unit, Teacher B gives out a survey and directs the unit using the information. So there was a question here. It says, what disease, health condition are you most familiar with and why? And a student posts diabetes. And then the next student says sickle cell and mentions pregnancy. And another student lists a bunch of STDs, HIV, et cetera. And that's the driving force of the unit. It also doesn't hurt that this teacher incorporates a little pop culture, and these were the patients. So every year they kind of changed with the flow of the classroom, okay? You gotta see what they're into. All right, so which class is best preparing students to become future scientists and critical thinkers? Okay, just think about that for a moment. And then I'd also like you to wonder, well, who are these teachers, Teacher A and Teacher B? right? Well, I'll start with the latter. Teacher A was me 8 years ago, okay? Teacher B is me today. And that was when I was 21, entered the profession, pretty naive about the profession, modeling my pedagogy around what I was used to, which was the teacher-centric model. Nothing wrong with it, but I thought what worked for me could certainly work for everybody else. I mean, why not? Couldn't have been more wrong, okay? Walked into my classroom, extremely heterogeneous in terms of racial profile, the economic profile, social, emotional profile, reading levels, and I realized I needed to investigate ways to make my class a little more engaging. I knew I couldn't change my student circumstances, but I could change the way that I teach. And so I started to do a little research on what makes a classroom engaging, and these were the 3 factors that I tried to incorporate more into my lessons. The first one being narratives, the second role play, and the last cultural relevancy. And in this research, I found that narratives tend to really help our students learn because it elicits emotions that can connect to characters. They're invested in them. In this case, it would be the celebrity patients. I also learned that by taking the material that you would get in a textbook and turning it into a narrative, it helped my students conceptualize the abstract ideas a lot better. And then lastly, I mean, who doesn't like a good story? It's so easy to repeat a great story. In fact, that was a great presentation before. I'll probably share it with my colleagues. But you can retain the information a lot longer rather than just regurgitate facts. And then the second piece, role play. Obviously, in this particular example, them being doctors, they're exposed to new identities and new career possibilities. And the way in which I usually set up my labs, which is usually 4 in a group opposed to the typical 2 lab partner, it helps refine their communication, collaboration, and leadership skills. And then finally, the cultural relevancy. It's really important to validate what our students bring into the classroom. And if you can do that, you're going to build their confidence, and they're more likely to be engaged. All right, so how does one pull this off? Because you're probably saying, this looks really complicated. How am I going to do this? So what unit? So I chose my anatomy and physiology unit. And with this, I just listed a bunch of concepts that I knew I needed to cover in this unit. And then I didn't reinvent the whole wheel. Go onto the internet, look up these concepts, see what activities there are, pick the ones you like that you think are going to be pretty interesting, and create a story around it. In this case, I created the story that they're going to be doctors. Bring in a little cultural relevancy. This time I chose the diseases that my students knew. I chose the pop culture component. And then I decided how I was going to assess them, which was a proper diagnosis after they did all their labs. Okay? So the next thing is, well, can you apply this to anything else besides anatomy and physiology? Absolutely. I did this with my ecology and human impact. So if you take a look here, I found the concepts that I needed to cover, found some cool labs that I wanted to do from online, and then the story is basically Avatar. My students actually watch Avatar and live through the Avatar characters and do the labs that associate with different scenes of the movie. Similarly, forensics, I relate this around CSI, either episodes. My students solve mysteries revolving around the teachers. We get the teachers involved, and my principal is involved in it as well. And similar format. I just use this format over and over again in all the different units that I do. So if you don't teach living environment, now you're probably saying, okay, Nicole, how can I do this in chemistry? How can I do this in physics? And how can I do this in math? Well, I'll prove it to you. I'm not going to give you the answer, but I want you to think about what story do you want to tell in your classroom? What identities do you want your students to take on? And certainly just, how can you connect the material to their lives and make it relevant to them? And if you're not sure, just ask them. I mean, that's the best way. Don't be scared to ask your students questions of what interests them. Now, on my blog, about a year ago to date, this was December 5th, and I do have a blog. I'll share my website with you guys shortly. I felt really validated with what I was doing because a teacher up in Buffalo, New York, who I'd never met in my entire life, downloaded my material off of my website. And she wrote, "Today we completed the review of the patient medical records in our class in Buffalo, New York. I have never in my career had students so engaged on a task. They absolutely are in love with this unit. It shows the power of making science relevant to the students that you teach." And this inspired me to sit down and write and write and write some more, edit, and edit some more, thinking I could go wide, nationwide with this. And I did. And actually, NSTA Press published it April 2013, this past year. So it's now available. And my goal now is to create more of this because it is becoming very successful in the diverse classroom that I teach. And I'm going to leave you with this, okay? I know we tend to get stuck in our ways, right? We've all been teaching many, many years. We we're very comfortable in what we do. But I really encourage you not to be afraid of change, because disrupting homeostasis when it comes to the mind can actually be a really good thing for your teaching. And on that note, I'm going to end it there. So thank you for listening. I appreciate it. And this is the website, if anyone's interested. Thank you.
Thank you, Nicole. Next up, we're going to hear from a teacher who's been teaching more than 20 years at the same school at Hunter College High School. And she is going to be leading us through some different ways to measure distance. So it's my absolute pleasure to introduce Sheila Krylov, who will be talking to us about New York City distance metric.
Hi. Okay, to the mathematicians in the room, to the physicists, displacement is a way of measuring change. Distance is the magnitude of that displacement. And I think tonight we'll explore what happens if we change our distance metric. Okay, so I am technologically challenged. I'd like to present a brief introduction to a non-Euclidean geometry developed by Hermann Minkowski in the late 19th century. He was one of Albert Einstein's teachers, just to give you a perspective. And we'll start by saying, what is taxi distance? Motivated by a Manhattan grid where we have north-south and east-west streets. Instead of measuring our distance between 2 points as the shortest distance as the crow flies, we will now measure distance only traveling on horizontal and vertical line segments. So taxi distance is the shortest possible distance between 2 points if you can only travel on vertical and horizontal line segments. First change we notice. Euclidean distance, there is only one shortest path between these 2 points. Taxi geometry, there are many, many shortest paths from point A to point B. You can go directly 5 points east and 3 blocks north. You can follow the solid green path. You can follow the purple dash path. They're all 8 blocks long. The taxi distance from point A to point B is 8. The combinatorists in this room may count the number of different 8-block paths from A to B, but that's for another talk. Okay. If we look for a formal definition, we're adding up all the horizontal distances. That's the difference between x2 and x1. We're adding up all the vertical distance. That's the difference between y2 and y1. So the taxi distance is the absolute value of x2 minus x1 plus the absolute value of y2 minus y1. And I've juxtaposed that with the standard Euclidean formula that we all remember fondly based on the Pythagorean theorem. To give a simple application, one suitable for your middle school students. Suppose there's an incident at the corner of 21st Street and 5th Avenue that requires immediate police attention. There are 2 police cars in the vicinity. Let's say it's 3:30 in the morning and there's no traffic on the streets. Car A is 3 blocks east and 4 blocks north. Car B is 6 blocks due west. Which car should the dispatcher send to the scene? Time is of the essence. You're sitting there saying, I remember, that's a Pythagorean triple, 3, 4, 5. Car A is 5 units from the scene of the accident. And then you say, wait a minute, but car A can't travel through all those tall buildings. The distance for car A to the scene of the incident is actually 7 blocks, the shortest path car A can take. Whichever way he goes on the grid is 7 blocks. Car B is only 6 units away. So this is a simple application of taxicab geometry. Next question we might start to ask, does taxi distance ever equal Euclidean distance? Well, in this example, we see that for car B on this horizontal path, taxi distance and Euclidean distance are the same. And in fact, on any horizontal or vertical line, taxi distance and Euclidean distance are exactly the same. But can taxi distance ever be less than Euclidean distance? Well, if those 2 points are not on the same horizontal or vertical line, Euclidean distance is d. Taxi distance is a plus b. Triangle inequality, a plus b is greater than d. No, the taxi distance is never less than the Euclidean distance. Next thing I'd like to address are a couple of locus problems that we consider as we develop geometry in any geometry. First locus I will ask about is, what is the locus of points at a fixed distance from a given point? For example, where are all the points that are 4 taxi units away from the origin? That would be the navy blue diamond. Because 4 points from the origin, you can walk 4 blocks due east, 4 blocks due north, you can walk 3 blocks in 1 block. And as we develop taxicab geometry, we no longer insist that this be the true Manhattan grid model. We allow for non-integral distances, so you can walk 2.5 blocks east and then walk. So we're no longer we can now go through these buildings magically. Anyway. The orange diamond shows all points whose taxi distance from point P is 2. And if we're talking about points that are at a fixed distance from a given point, we're talking about circles. And taxi circles become diamonds. So a next avenue of inquiry might be, well, in Euclidean geometry, there's a constant ratio of circumference to diameter. And if you haven't done it with your middle schoolers, get some string and some circles and measure circumference, diameter, and let your students compute that ratio. And they should be getting something very close to pi. That's how pi is defined. What happens in taxi geometry? In taxi geometry, we still have a diameter of 2r. But our circumference is made up of these 4 slanted segments. Each slanted segment goes r units horizontally and r units vertically, which means the length of any one of these slanted segments is 2r, giving us a circumference of 8r with a diameter of 2r. And yes, we still have a constant ratio, but now that ratio is 4. While you're doing some explorations, kids love looking at pictures that are colorful. And if we look at the green shaded region is all points that are less than 2 units from point P. The purple region shows all points that are more than 5 units but less than 7 units from point R. And the diagrams can get very pretty. The next question I'd like to ask is another locus we study in Euclidean geometry. What is the locus of points that are equidistant from 2 fixed points? With some prodding and some exploration, every student's going to say the midpoint of that line segment. With a little bit more prodding and investigation, you get the perpendicular bisector of the line segment in Euclidean geometry. What happens in taxicab geometry? Well, the first case is pretty simple. If the 2 points P and Q are on the same horizontal or vertical line segment, we still have the perpendicular bisector. But the story doesn't stop there. If we move to 2 points where the P and Q are on a line segment with a slope of 1 or negative 1. So in this example, I have the points 0, 4, and 4, 0. Euclidean geometry, I have the perpendicular bisector of that line segment. When I switch to taxicab geometry, something remarkably different happens. I'm still on the line y equals x in this square. But once I get to point R, every point that is to the right or above point R is equidistant. It has the same distance to point R, same taxi distance, and therefore is equidistant between P and Q. Likewise, every point that's to the left or below point O. And so we get this absolutely unique locus, and that works. But this is only case 2, because we can either be on the same horizontal or vertical line, we can be on a line of slope 1 or -1, or we can be what taxicab geometers call shallow or steep lines. The shallow lines having slope whose magnitude is less than 1, and steep lines having slope whose magnitude is greater than 1. So let's look at a case where we have a shallow line. So I've chose the points 4, 1, and -4, -1. Euclidean geometry, we have the perpendicular bisector. It goes through the origin. PQ has a slope of 1/4. The perpendicular line has a slope of -4. When we go to taxi geometry, something very different happens. In this rectangle, defined by these 2 points, the origin is still on this line, but that's the only point it shares with the Euclidean model. We're now on a line with a slope of -1 within that rectangle. And then we have this perpendicular, this vertical shoot up, vertical shoot down. And so we have a third case. If we had a steep line instead of a shallow line, you just rotate it 90 degrees and you'd get a horizontal zigzag. Last aspect of taxicab geometry I'd like to mention in my 10 minutes is congruent triangles. Let's go back to classical geometry. You have all these wonderful axioms. 2 triangles are congruent if they agree in side, angle, side, if they agree in all 3 sides. What happens in taxicab geometry? If you look at the purple triangle and the turquoise triangle, they are 2 congruent right triangles. They both have hypotenuse of length 8, legs of length 4, radical 2. One is a rotation of the other, rotation translation. If we go to taxicab geometry and we measure the sides of these 2 triangles, the purple triangle has 3 sides of length 8. Watch. This is clearly length 8. To go from O to T, I'm going over 4 units and up 4 units. So my taxi distance is again 8. Likewise, to go from T to P, I'm going down 4 and over 4. So this purple triangle in taxi geometry is equilateral and right at the same time. And something even more bizarre happens in the turquoise triangle. In the turquoise triangle, the horizontal and vertical line segments have the same length as Euclidean geometry, namely 4 square root of 2. But now the hypotenuse is 8 square root of 2, and the triangle inequality fails in this triangle. If I have intrigued you and you're interested in learning more about taxicab geometry, do a Google search. There are wonderful articles that pop up right away, lots of really accessible worksheets that are almost ready to use with your students. And at this point, I'd like to say, I hope you enjoyed the ride. Keep the change. Thank you. Thank you. Make sure your mic's on. I will.
Thank you, Sheila. That was wonderful. Before I introduce our next presenter, who's going to take us home before intermission, I'd like to just thank the Math for America staff who's here tonight. If you are a Math for America staff, would you mind just raising your hand so everyone can see you? Thank you for being here. And a special thanks to Sharika and Julie and Josh, who are outside, very actively taking away dumplings and putting out cookies. So if you arrived and didn't have time to eat, there's plenty of leftover dumplings, I'm quite sure, and there will be cookies at the break. I thought it was wonderful that we had Sheila talking to us about a different distance other than our Pythagorean distance, because tonight we're all come together on a Pythagorean triple. So it's December 5th, 2013, 12/5/13. So extremely appropriate. Thank you, Sheila. Without further ado, I'd like to introduce the final speaker before intermission. Patrick Honor is going to be talking to us about change. And Patrick is a teacher at Brooklyn Tech, and he was a presenter last year at MT Squared, and so we're very happy to have him back. Welcome, Patrick.
Thank you. Thanks. Is this on? Can you on? Okay. The homeostasis of my mind has definitely been disrupted by that taxi cab geometry. I paid a little too close attention to it, so just you might have to give me a minute or two on some of these slides. So when the theme was announced, change, I was excited because change is such a big idea, but it's one that I think we as teachers are really well suited to address because we deal with all different kinds of change all the time. The way we teach is changing, and the way we learn is changing. As Noah mentioned earlier, we all know policies change and politics change. This is my favorite picture of the year. Then there's the whole idea of mathematical change, which is something that's, I think near and dear to all of us, even our non-math teaching colleagues. Welcome. And these days, I can't hear the word change without thinking about changes in lifestyle. But I kept coming back to an idea of change that was really meaningful to me, both as a teacher and as a mathematician. So today I'll talk to you a little bit about my profound relationship with change. I really do have a deep mathematical relationship with change, one that has endured throughout my entire life. I remember as a kid loving to collect and count and sort and stack change. I remember getting excited about figuring out congruent piles and measuring that way, or breaking things into congruent piles to divide them equally. I liked exploring notions of equivalence and different representations of numbers using change. And apart from like the numeric stuff, there's the geometry of change, because these things are little circles in your pocket. And you can't help but want to arrange them in like these sort of mutually tangent ways, or in little rectangles, or maybe more efficiently like this. And so, and then of course there's the whole sort of practical side of change, right? The way that I would use change to interact with the world. Like there were things I wanted, so I would I'd save up my change and I'd get excited to go get things, and then I would sort of try to predict what kind of change I would get back and what denominations I would get back. In fact, as I thought about this, I realized that one of my earliest, I think, sincere mathematical problem-solving experiences was with the idea of exact change. Like, I remember thinking to myself, if I always want to pay an exact change, what do I have to carry around with me? And I think this was probably like my first experience with extreme case thinking. Like the worst possible cases, I have to pay 99 cents. So I need to be able to make 99 cents. But then you think it through and you're like, okay, well that's good. So I need to carry 99 cents, but I also need to be able to make everything else. Like I need to be able to make 9 cents. So you need a little more flexibility. And then and this problem about paying with exact change sort of evolved as I got older. Like quarters became really important to me for like the arcade, or later for laundry. So I wanted to make sure that I always had change in my pocket so I could get quarters back. So that was like another problem that I solved. So like change really fostered a lot of mathematical thinking for me as a young person. And even now, recently my piggy bank was full, and I thought, how could I estimate its value? And I thought, well, maybe if I weighed it, and if I knew the weights of coins, maybe that could give me an estimate. But then I realized that I would need to know like the distribution of coins, which got me thinking like, what's the distribution of change? And so I created like this mathematical model of trying to figure out, like in a random stack of change, what should the distribution be? And so I ended up writing about it, thinking about it, doing some analysis. And it really created like a lot of interesting conversations with colleagues and students about whether my model was appropriate. And then after a year or two, my change filled up again. This is an old Royal Oak rum case sent to me from by my father. So this filled up, and I thought I'd take a more statistical approach. So I took a bunch of samples of the change to see if I could use that to predict the distribution. And a lot of interesting questions about sampling technique sort of came out of this. Like, if I was sampling with my hand, is that biased towards getting large coins because those are easier for me to grab? Or if I scooped coins out, would that bias small coins because those were easier for the scoopers? So yeah, like I've had a lot of interesting experiences with change even recently. Change has also made its way into my classroom. Students really annoy me by drawing their diagrams really small. So I created a policy on tests that if I can cover their diagram with a coin, then I don't have to grade it. Now, they didn't take me seriously at first until I started walking around jangling coins. And now they take me very seriously. And they actually bring coins with them when they're taking tests. And sometimes, you know, we like to mess with our students, right? Sometimes I'll just carry a 100 colones coin in my pocket because that's bigger than a quarter. And, you know, we like to keep them on edge, right? So obviously I had a lot of fun thinking about change. I never really thought about it this deeply before, and it was nice to have the opportunity to do so. Because it was fun. I realized that sincerely, like it's had a very profound impact on me as a mathematician. As a teacher, a couple of things I saw thinking this all through was that there's really a lot to be gained by thinking deeply about simple things. Like, I think as teachers, we're conditioned to kind of think broadly. We think, what am I teaching today? What am I thinking tomorrow? What am I teaching tomorrow? What do I have to teach, you know, by June? We don't have a lot of time to think deeply about simple things. But just something as mundane as thinking about, change got me thinking about equivalence and partition and unique and non-unique representation, about tangency. When is it possible? When is it not? And about, efficiency, like how to efficiently pack circles is a very deep mathematical question. And it also got me thinking about how, and something we all know, how important passion is as a teacher. I get excited about paying all of my tolls in exact change. Toll booth operators do not enjoy it so much. But yeah, this is something I enjoy thinking about and writing about, sharing with my students, or thinking about the ideal distribution of change. And so, it's very good for students to see that passion. And when it comes to students, one thing it reminded me of is that, again, something we know, but something that, needs thinking about every now and then, is that our students are different than us, and my students are different than me. Like, they don't have the same relationship with change that I did, because candy bars don't cost 35 cents for them, or they don't have paper routes or whatever. So it's like not part of their life the way it was part of mine. And so they're a little bit, so they bring different experiences, both personal and mathematical, to our conversations in the classroom. And that, reminds us that as teachers, of course, we know that we always have to adapt and change. Thank you very much.
Thank you very much, Patrick, and thank you to all four presenters. We're going to take a 15-minute intermission, and we'll be back in just a few. Enjoy the cookies.